Welcome to the FEMAP 10.2 What's New video series. In this video we'll take a look at topology optimization.
I'd like to walk through a little example of using the new topology optimization module in FEMAP version 10.2. I've got this part here that kind of represents the outer volume for a little torque linkage. We're going to let the topology optimizer determine what shape we should actually make this part of. So first thing we'll do, it's a regular finite element model, so we're just going to take this piece, apply some constraints. And what I'm going to do is just pinned through the holes here and on the boss on the end where the torque load's actually going to get applied. So I'm going to go in here and just create a new constraint definition on surfaces and pick basically the circular surfaces here, and we'll set those up for we won't let them constrain grow radially, and we won't let them slide. So basically these are just going to allow them to torque, rotate around their axes. So there's our constraints, and let's go ahead and throw a load on here too. I'll say new, and I'll call this positive torque. What we're going to do is go in here and open up the load definition, create a new load definition on a surface, and we'll apply our torque load right there. I'll do a new, this is actually a torque load we added just a couple of releases ago in FEMAP, but we'll do 250 inch-pounds, and I'll say OK, and it asks me for a vector. What I want to do is do a global Y vector, and then I want to pick the center of that surface. So I can hit Control Z, brings up the standard coordinate box that has a method that's the CG of a surface. So I'll pick the CG of that surface there. It fills it in for me. I can do a preview and say, yep, that's the right vector. And I've applied my torque. Nice thing we can do here now is I'll just copy this to a separate, another new load set. And I'll just go in here and do a little renaming work and just call it negative torque. And then I'll actually go in and just edit the load definition. That's just a copy of the other one. Edit the load, and I'll just make it a minus 250, and this will give me the opposite direction. You do want to be careful when you're using the topology optimization that you do include all the load sets that your part might see. This way, you're basically optimizing. If you don't consider all the load sets, you could get some shapes that probably wouldn't be optimum for some other different type of loading, so you want to get them all in here. Since this is a torque thing and we've got everything set up, it's just going to twist one way or the other. Let's go ahead and mesh this. I'll just open up my geometry, pick my one part and say mesh, and we'll just make him out of aluminum. Say OK, and just let the mesher fly. So now we've got our model ready to go. I'm just going to go ahead and save it and set up the analysis. This is just like setting up any other analysis in FEMAP. We are optimizing here for the torque loading here, so we do want to set up both of those load cases. By default we get just the current active one, so I'm just going to turn off the master load cases here and use our multi-set to create, for the one constraint set we have and all the load sets we have, create subcases. And I'm also going to set up our topology optimization run. So I just want to say yes, we're topology optimizing. I'm going to include all elements. You could actually include just a group of elements and only optimize in a certain area. But we want to go ahead and optimize the whole thing. And I'm going to try to take out 50% of the mass. I'll set that as my goal. And we are trying to maximize stiffness and reduce volume. There's also, for frequency or modal runs, you can actually try to optimize for a maximum frequency and stiffen your part while reducing volume. Or actually set up a volume constraint with a maximum displacement. But here we just want to make it as stiff as we can and reduce volume. Actually, did I lose my 50% there? Let's make sure. Let's say OK. We could freeze groups. You could do some wall thickness things. Set up some casting directions. And in this case here, I think we're just pretty much going to let it go and let it run. Alright, let's go ahead and run this now. Hit the Analyze button. What this will do is spark off the analysis. This actually runs Nastran multiple times, and looking at the results of each run and basically doing some work on the stiffnesses of the elements and basically carving away parts of the part. We can actually watch the design objective change. So after 2 runs of Nastran here on this part, we should start seeing some changes. So the stiffness will show up and the volume constraint. So the volume's already been dropped down to 82% of original. The design objectives, which would be the maximum stiffness, which the full part was this. It's basically keeping the part almost as stiff as it was. We'll just let this keep running here. It's already through 3 iterations. I may actually edit the video and carve out some of these so you don't have to watch them, but it's not going to take too long here. You can see it's progressing along nicely. Design objective is still maintained real well. We're still at 99.5% of the original stiffness. The volume's down to 63%. Remember, we're shooting for 50% reduction, so we'll just let this run. Alright, the model's done here. We can see that the our design or volume constraint was met with a pretty much a 50% reduction in the volume of the object. And the stiffness stayed right up there at 98.9%, so our model's pretty much as stiff as it was. I'm going to go ahead and shut this down. Now, the topology optimization, you got to remember, this is pretty much a recommendation for a design modification that will remove some mass from your part. So obviously the lugs here, we're not going to take them completely away. That just doesn't make any sense. But it looks like the middle here, we can certainly get away with it. And if you look up the inside here, you'll notice, let me turn off all the geometry. So we just have the mesh here. You notice it actually started carving in up the muddle. So it's actually suggesting to me design modifications should be to basically hollow this piece out, take off some of the edges here, and leave the rest of the part. So what we've done is we brought in here, these are plot-only elements in FEMAP. They're just highlighted right now. So I'll go ahead and redraw the display. But we can use some of the visualization tools in FEMAP. I'm just going to turn off the original solid elements. I'm looking at just the resulting topology optimized mesh or shape, and actually go into a wireframe view, and you can see that it's showing us how to carve this out up the middle. Now, obviously this is a pretty free-form shape. It doesn't make a lot of sense for design, but what I did is obviously I've already run this once, but I used these results to bring in and edit the geometry to kind of come up with a better shape. So you can see here, this kind of what you might do with the results here is say, it's telling me to hollow it out the middle, carve off the edges. A bunch of material here really wasn't needed, so my volume can be reduced a lot. We'll just do a little geometry check here. Let me turn my surfaces back on, go into a solid view. We can just do a quick mass properties on our solid here, and I can pick that solid and say OK. And I'm just going to put in the density as 0.283. So it tells me I got a total mass of 27.8. I can pop over my other model, do the same thing. So here's my reduced design. Solids, pick him. Don't need a node. We're not modeling that right now. 0.283. You can see here we got a pretty nice reduction in overall volume from mass from 27.8 to 18.4, and you remember the stiffness really wasn't affected that much. So it's a fantastic tool for helping you optimize the shape of a design.